So here, maybe I will just solve maybe 2 or more 3 questions because we didn't have that much time in the tutorial. So please, whenever you are free, just watch this video or record it. Watch it whenever you are free. And if you have any question, come back to me. I will explain it for you, inshallah. So the question that I was trying to solve is this one. I want to solve this question. It's in your homework, I think. Okay. So he's saying that what is the minimum diameter at section 1? Here is section 1 to avoid cavitation. So again, we have a cavitation question. At that point, take D2 as 15 centimeter. He gave you the diameter at point 2 as a 15 centimeter. Now there's something missing in this question, and that is the temperature of the water, because in order to know what's the cavitation pressure, remember what's the saturation pressure. P saturation, or the cavitation pressure, is equal to P saturation at a given temperature. So you need to be given the temperature in order to determine what is the saturation pressure or the cavitation pressure. So here, assume the temperature is 30. Okay, assume the temperature is 30 degrees Celsius. Now, according to this temperature, I can go, just as I explained for you in the previous tutorial, go to the book, edition 4 or edition 3, whatever edition you have. You have appendix 1, go here to appendix 1, or just go to page 247 in the PDF. Okay, and then just go few pages. You will find here table A3 in page 250, and 950. Okay, here you have the set of the temperatures and the corresponding saturation pressure. Our temperature is 30, therefore this is the saturation pressure here, 4.246 kilopascal. Okay, so we'll just write it there, 4.246. 4.246 kilopascal. Okay, now here we also need to know, just like the question that I solved in the first tutorial, where cavitation will occur in this system. Cavitation, remember cavitation, like you have a pipe, right? You have a piping system. Okay, whatever the shape of the pipe, you have this way and then this way, whatever. There is a point, there is somewhere in the pipe where the pressure will be minimal in the system. Assume, for example, this here. And therefore, if cavitation occurred, if for some reasons pressure low value happen here, because this point is the point where the lower pressure exists, and therefore if cavitation occurred, meaning that the pressure dropped below this value, then it will be at that point, the point which is associated with the minimal pressure in the system. Okay, so here, where is that point? Of course, it's point 1. Why is that? Because point 1, it has the what do you call it? Less cross-sectional area than 2, right? The area at 1 is less than the area at 2, and you remember Q is equal to Q, so A1 V1 is equal to A2 V2. Okay, and if the area at 1 is higher, then the velocity is lower, and the area of 1 is lower, then V1 is higher, And here the inverse. A2 is higher, the cross-section area at 2 is bigger, and therefore the velocity is lower. And if the velocity is higher, then the pressure at 1 will be lower, because if you apply Bernoulli equation between point 3 and point 1, and between point 3 and point 2, okay, both are at, so the left hand side is P3, or the atmospheric pressure, because you have this, okay, P3, and the fluid here is stagnant, I mean no motion here, so we don't have the dynamic term, which is half rho v squared, because there's no velocity. And then we have the hydrostatic rho g h here, 5, okay, because it's at an elevation of 5. Assume this will be the datum, okay, or my reference, and it's equal to the pressure here, either in 1 or 2, just call it the pressure, and then we have a dynamic pressure v squared, and then I don't have hydrostatic because those points are at my reference, so there is no rho gh. Okay, so if the velocity of this point, if the velocity is higher, then of course I'm increasing this term, then in compensation I need to reduce this term because the mechanical energy is conserved. Cannot just increase this one. You can increase it, you should decrease this one. So whenever you increase V1, because V1 is higher than V2, so V1 here is higher than V2, then P1 is less than P2, okay? And this applies also for any point here. Not necessarily one exactly, any point that has the same cross-section here. Because if you apply Bernoulli equation for everything here, it's the same, at the same elevation, we have the same cross-section area, so you have the same Bernoulli equation. And for this, here the cross-section start to vary. The area start to increase until we reach here the maximum area, and there maximum area, it's associated with the maximum pressure, P max. Because higher area will be associated with lower velocity, and lower velocity here meaning that you have higher pressure. So we can conclude that this section is the section that where the pressure is lowest, because highest velocity, lower pressure. The pressure is lowest, and cavitation can occur here at this section. Not necessarily point 1, any point here. Okay, so this is our first conclusion. And yes, another thing, maybe here someone will ask me, we said Bernoulli equation, not only on this question, any other question. We said Bernoulli equation is applied along a streamline, right? So here you'll ask me, where is the streamline exactly? When you apply it between point 3 and 1, for example, you can assume that like this point, the water here will go down, and then it will enter through this gap and reach here. And then the streamline will become straight. So you can assume this is a streamline, and I apply between point 3 and 1 or point 3 and 2, okay? So now you know that the cavitation pressure will occur here. You can substitute this pressure, assuming that cavitation will occur. Cavitation, maybe it will occur, maybe no. Now, if you substitute this cavitation pressure here, meaning that you are on the verge of cavitation to happen, or just cavitation occurred, or something like that. Because you want the diameter that will cause cavitation, or in another word, you can say the minimum diameter to avoid cavitation. That it's the threshold. Because if you reduce the diameter below the value here that you will obtain, cavitation will occur. So I will consider that there is a cavitation, and I will find the corresponding critical diameter. If you reduce the diameter lower than that, the velocity will increase, the pressure will decrease, and it will go below this one that I will substitute in Bernoulli equation, and thereby cavitation will occur. Okay, so applying Bernoulli equation, we have P3 is the atmospheric, 325, and then I will add Raw of water is 1000. You have 9.81. And you have 5, the elevation. P2, assuming that cavitation will just occur at 0.1, because the pressure is the lowest there. Sorry, here you need to multiply it by 1000, because this is kilopascal, so you don't have point here. 4246 multiplied by 1000 here, so you'll shift the decimal 3. Okay, and then plus half, the density is 1000, and you have V1 squared. Find V1. Okay, V1 is equal to, just let me substitute it. Okay, V1 is equal to 17.1 meter per second. Okay, now I found the velocity at 0.1, but he wants the diameter at 0.1. So how can I go from a velocity to a diameter? What's the link between them? The only link between them is the flow rate Q or V dot. Therefore, if I know what's Q or V dot, I can move from the diameter from the velocity to have the diameter or vice versa. Okay, so how can I find the flow rate? Again, you can apply Bernoulli equation between 0.3 and 0.2, because 0.2 here is like this is the end of the what do we call it? The end of the pipe, and then the water will start to go out. Okay, and will start to go out of the pipe. The pressure that will be imposed here is the atmospheric pressure again, PATM. Okay, so you have the pressure here, and you can find the pressure is the atmospheric, just like the 0.3, and then you can find the corresponding velocity at 0.2. So you have P3 plus rho G H3 is equal to PATM, or the atmospheric pressure, which is at 0.2. Okay, this is 0.2, this is not a square, plus half rho V2 squared. Now you have here the pressure is the atmosphere, okay, the pressure are the atmospheric at both sides, so just cancel them. So you have rho G H5 is equal half rho V2 squared. Okay, V2 is equal to 9.905. Okay, meter per second, and I am given in the question the diameter at 0.2. Therefore, I can find D2 is equal to 15 or what? 15 centimeter. Okay. When you multiply the velocity by the area, which you can find it from the diameter, you will find Q, the volumetric flow rate, which is equal to 9.905 multiplied by D squared, 15 centimeter, meaning that it's 0.15 meter squared by 4. You have a value for the volumetric flow rate. Then, after you obtain this volumetric flow rate, divide volumetric flow rate that you will find here by V1 to find A1. V1 we found it in the previous step here, 17.1. Okay. When you find A1 is equal to by D1 squared by 4. So from this step, move to this step, you find A1, then equate A1 by this to find D1. Okay, and by this you will solve it. Okay, moving on to another question. What we have? Okay, check this one. You have air is flowing through a venturi meter whose diameter is 2.6 inch at the entrance part, location 1 here. Okay, and at location 2 he also gave you the diameter. The gauge pressure is measured to be 1.22 pound per inch squared at 1 and 11.8 at 0.2. Neglect the friction effect. See, whenever he say neglect the friction effect, meaning that Bernoulli equation, the use of Bernoulli equation is justified because this is one of the conditions. Frictional effect is negligible, meaning that the flow is inviscid. Inviscid, meaning that frictional effects are negligible. Okay, and even if he didn't say that, you can assume this because you don't have another way to solve it. You always need in this chapter to apply Bernoulli equation. So always we will assume the flow is inviscid, the flow is steady, and the flow is compressible or incompressible. Yeah, you need to check if it's air. You need to check Mach number. If it's fluid like oil, water, anything liquid, then you can directly assume it's incompressible. And you can pick a streamline and apply Bernoulli equation along it. Okay, so anyhow, what's the question? Show that the volume flow rate can be expressed using this equation. Okay, I will just solve this part and then the second part is just to substitute. Okay, because he's giving you everything here, just substitute. So now I will only care about how to find this relation of the volumetric flow rate. Okay, so you have this, like try to draw it. Okay, something like this. Okay, assume this is 0.1 and this is 0.2. Okay, and the flow is going this way. This is my streamline. And I will apply Bernoulli equation, given that the flow is inviscid. It's inviscid and it's incompressible and the inviscid incompressible, and I apply it along the streamline and it's steady. And you can check here because it's air, you can check for the compressibility condition that I showed you. Divide the velocity. You have the diameter here, right? You have the diameter and what else? You have here the diameter at 1, the diameter at 2, and you are given the pressure. So, okay, here you cannot apply it directly because you cannot find the velocity here. You need to find the volumetric flow rate first. Then from the volumetric flow rate, you can divide it by the area. This is the volumetric flow rate. We will now develop this equation. After you find it, you can divide this volumetric flow rate by the area here. You have the diameter, and then check the velocity. If it's turned out to be less than 0.3, sorry, the velocity, if it turns out to be less than 100, which corresponds to Mach number of 0.3, then you can say the use of Bernoulli equation is justified. Otherwise, you can say it's not justified, but you have no option, so you just stick to it. Okay. So now let's see how can we find this volumetric flow rate. So applying Bernoulli equation between point 1 and point 2, you have P1 plus half rho V1 squared is equal to, okay, the cross-sectional here is different than here, okay? This is just a rough sketch, okay? P2 plus half rho V2 squared. And remember the last term rho GZ, you will drop it from both sides. Why? Because they are at the same elevation. Z here is exactly equal to Z here. Therefore, I'm adding just extra term to the equation, so no need for them, just drop them. Okay? In case Z does not equal to Z, no, you have to keep them. Canceling them is not correct. So, he wants to find the volumetric flow rate, okay? So, I need also to apply, this is equation 1. I need also to apply the continuity equation, which is A1 V1 is equal to A2 V2, which is equal to Q. Now from this equation, from equation 2, I can say that V1 is equal to Q over A1, right? Q over A1, and V2 is equal to Q over A2, right? Then you can substitute this one here. Once for V1 and once for V2. Why is that? Because I want this equation to contain the volumetric flow rate, because if you can see here the end result, I need to have the volumetric flow rate equal to some terms that are present in Bernoulli equation like P and P. Okay, and you have the area here, meaning that you remove the velocity, there is no velocity here, and you will substitute it by the volumetric flow rate and the area, and therefore you have here some areas here and the volumetric flow rate. So this is what you need to do, and P1 and P2, they are present here, okay? So P1 plus half rho, now V1 is equal to Q over A1 all squared is equal to P2 plus half rho, now V2 is equal to Q over A2 squared. Am I sharing the screen or no? Recording. Yes, I'm sharing the screen. Okay, good. So now, what we have here in the equation, we have P1 minus P2, right? So just rearrange the equation, bring P2 to the other side, so that we have just like the end result, P1 minus P2. Okay, and bring whatever else to the other side, bring this one here. So you have half rho, take half rho as a common factor after you move this term there, and then you will lift up with Q over A2 squared and minus Q over A1 squared. Okay, also you can take Q squared as a common factor, because here, yeah, you have P1 minus P2 is equal to half rho Q squared, take it as a common factor from here, and then you have 1 over A2 squared, distribute the power to the denominator and the denominator, Q, but take first Q outside. Okay. First distribute the power, so you have Q squared and A2 squared, and here you have Q squared and A1 squared. Then Q squared, take it as a common factor with rho and half. Okay, so you have 1 over A2 squared minus 1 over A1 squared. Okay, now I want to find what's Q here. So I need to divide by those terms the other side. So you have P1 minus P2, then multiply both sides of the equation by 2 to get rid of this half. So I multiply it here by the pressure. And then divide by this bracket. Divide this bracket here by P1 minus P2 to move it to the other side and isolate Q in the left side. So you have here, you will divide by 1 over A2 squared minus 1 over A1 squared. Okay, and also don't forget the rho. Here the rho, so how can I get rid of it? I need to divide P1 minus P2 by rho. So here you will have also rho. And at the end you have the square root because you have Q squared. Okay, now still we didn't reach this one exactly. It's equal, but how can we make it the same? It looks very similar like this one. Okay, we need here to do one thing. You can multiply the denominator and the denominator by A2 squared. Look what will happen. You have 2 here multiplied by A2 squared. Okay, multiplied by P1 minus P2. Okay, and the denominator you have rho, and then I will multiply it by A2 squared, and then the remaining 1 over A2 squared minus 1 over A1 squared. Okay, I'm multiplying the numerator and the denominator. It won't differ because you can cancel them. But I did this because I want to change the form of the equation, but at the end it doesn't change the equation because I added at the denominator and the denominator. It will be cancelled. So this one, A2 squared, what is the square root of A2 squared? It's A2, right? So you can take it outside of the square root and take the root of it. The root of A2 squared is A2. And then you have the square root 2 by P1 minus P2. And the last step here in the denominator, you have rho, and then distribute this one. So you have A2 squared by A2 squared is 1 minus A2 squared by A1 squared. Which is exactly what is given here. Okay. Then substitute the numbers. You have just the numbers, substitute them and to get Q or V dot. But the most important thing is that we reach this one. Okay, so let's look at another sample. I will just go here to one of the questions in the back. Okay, look at this question. Here he said the static and the stagnation are measured by a piezometer and a pitted tube to be 200 kilopascal. Sorry for that. Okay. Okay, the static and the stagnation pressure of the fluid in a pipe are measured by a piezometer and a pitted tube to be 200 kilopascal, this is the static pressure, and 201 kilopascal, this is the stagnation pressure, respectively. If the density of the fluid is 550 kilogram per meter cubed, the velocity of the fluid is, select the correct answer. So here if I want to draw it, or not, okay, let me try to find it here in your slides. Where is the piezometer and what's the pitted tube? You have it here. Yes, this one. This is the piezometer, okay, the one that will measure the static pressure. And this is the pitted tube, okay? The pitted tube will measure the stagnation pressure. You have exactly this configuration in the problem that we just read, okay? This is exactly the configuration. So And what's the you have here? You have two equations. One to find the velocity of the fluid here before it came to a complete stop here at the stagnation point. You can either use this equation. You can find the velocity in terms of the pressure difference, or you can find the velocity in terms of the height difference. The height here, h2 minus h1. You have two equations depending on what is given. So in our case, we are given the static and the stagnation pressure. So which equation? Of course, we will go with this one. I have the static, this is the static, and this is the stagnation. And he is giving me the density of the fluid, which is 550, and he wants the velocity. Okay, the velocity here. So just substitute, we have, let me write it here. You have the velocity is equal to square root of 2 p stagnation minus p static divided by rho. So he gave me 2. What is the stagnation pressure? The stagnation pressure is 201. So 201 minus the static 200. Okay, and multiply by 1000 to convert from Pascal to kilopascal. Because at the end I want the velocity in meter per second. So in meter per second, this is the SI unit. So if you want the output to be SI unit, you need all the inputs to be in SI unit. So therefore I will convert kilopascal to Pascal and divide by the density. It's already in the SI unit. 550. 550. Then you have square root of 200 minus 2,550. You have 6.03 meter per second, which is here. Okay. So this is also one form of the questions that may come. Let's solve one last example. Okay, here. Maybe this is the last one, or maybe we'll solve another one. Okay. You have two dimensionally identical containers are connected to each other by a pipe with a diameter of 3 centimeters. This is the diameter of the pipe. Container A initially contains water, but container B is empty. The cross-sectional area of each container is 4 meters squared. The cross-sectional area, okay. And what else? If the viscous effect are negligible. What do you mean by the viscous effect is negligible? Meaning that the flow is inviscid also. Viscous effect is negligible, meaning that the frictional effects are negligible and the flow is inviscid. Determine the time needed to empty the container A completely. Okay, so let me crop it. So I'm given the diameter of the pipe here, and I'm given the diameter or the cross-sectional area of the container. And what else? That's it. He wants to find the time needed for container B to determine the time needed to empty the container A completely. What's the time needed to empty container A? Now, when we ask you about the time, okay, he's asking about the time, and we want like the time needed to empty container A, meaning that the time needed so that like the volume inside the container A to be discharged, the entire volume of the water here to be discharged, okay, and become empty. So if you can find the volumetric flow rate Q or V dot, okay, the volumetric flow rate actually is the rate of decrease in the water level, or in the, not water level, the, like the rate of decrease of the water volume inside the container, and it is also the flow rate here that you know, which is V over multiplied by A, and it's also the rate at which this container is being filled. Okay, the rate that the rate of increase on the volume of the fluid in this container B. Okay, they are all the same. So if you are able to find the volumetric flow rate Q, you can find the time. Why? Because the volumetric flow rate is actually equal to, and in the pipe it is equal to V multiplied by A, but in the container it's equal to the volume of the container, the volume or the fluid in the container divided by the time, because it's, you know, it's the unit, it's meter cubed per second. Okay, so if you are able to find Q, then multiply, if you are able to find Q, then divide the volume of the tank by that Q, you'll be able to find T, the time. So now we need to find what's the volumetric flow rate. So how can we find the volumetric flow rate? So we applied Bernoulli equation. Let's assume we apply Bernoulli equation between point A here at the free surface of tank A and here. Just not at the exit exactly of the pipe, no, just like a little bit distance, this distance. See, we'll go just a little bit distance so that the exposed pressure is the atmospheric here, PATM. Okay, like it when this is the streamline, okay, and the point or the waters just went slightly after the pipe exit, and it's now exposed to an atmospheric pressure. Okay, B is empty now. Okay, still there's no water. So this is the water is coming this way until it go out of the pipe. Now it will be exposed to the atmospheric pressure, and its velocity will not change that much. Like the velocity of, like, this point has the velocity of the outlet of the pipe, but not the pressure at the outlet, because it will go a little bit. So now it will be exposed to an atmospheric pressure, and the velocity will not change that much. Okay, it's like the velocity at the outlet of the pipe. So you have PA, or the atmospheric pressure at A, and you have no fluid motion here at the free surface. Okay, and the elevation, assume this is our datum or our reference. So you have an elevation here for point A. So you have plus rho G ZA is equal to P here, this point, call it 2 or whatever. So I have here 0.2, which is also the atmospheric, plus, and this point is at the datum here. The point here is at the datum, so I have no rho G Z. You will just have the dynamic head, or the dynamic pressure, sorry, half rho V squared. You have just cancel those two because they are equal. You have rho GZA, you know the elevation of A, it's 0.5 plus 2.5, which is 3, and then 3 plus 0.7, which is 3.7. So you have 1000. Then 9.81 by 3.7 is equal to half, and then rho is also 1000, and then V squared is unknown, the velocity at which the water here will exit, and then the water will go until it hit the bottom of the tank. So the velocity here is approximately the same as here. So of course it's not exactly the same, but we don't have like another way to apply Bernoulli equation. So you need to assume it's almost the same, and the pressure will be applied by an atmosphere, because it will go, it will leave, it will be freed from the pipe. In the pipe, the fluid has a certain pressure, but once it exits the pipe, it is now exposed to the atmospheric pressure, just like point A. Okay. And point A, maybe you say like this, you draw this streamline. And how you say that point A is not moving, the velocity is very slow. The velocity is very slow here compared to the velocity in the pipe. Because you know, when you decrease the area, the fluid will move faster and faster and faster. You decrease the area, fluid will move faster. So here in the pipe, there is a considerable velocity. But here, even if there is a motion, it's like negligible compared to the velocity in the pipe. So that's why we always take the free surface as a zero velocity, as if the fluid is stagnant, there's no velocity, and it has the atmospheric pressure, it's exposed to the atmospheric pressure, and there is a certain elevation for the tank. Okay. So given this, V is equal to 9.81 multiplied by 3.7 is equal to half x. Okay, the velocity is equal to 8.52 meter per second. Okay, now this velocity, as I said, it is the velocity here, and I will assume that it is also, there will be no much change here, because what is the difference between this point, just the exit, just the exit of the pipe, and this point here? Okay, let me make it clear for you. So this point, just the face exit of the pipe, and this point where the datum exists. Okay, there is a small elevation difference, right? There's small h, tiny h. Okay, so if you apply Bernoulli equation again between those 2 points, what do you have? You have P at the pipe. This is not for solving, this is just to let you know why I'm considering them as the same velocity. Okay, and you have half rho V squared, okay, is equal to P plus half rho V squared, and also you have 0 here plus rho GZ, and here you have also plus rho GZ. Now the elevation difference is like approximately negligible, so just cancel them, and here you have the pressure at the pipe, okay, and just when you exit this point and come to here, the pressure will be atmospheric, okay, and assume that the velocity will not change that much, okay. So after we found the velocity, and as I said, there is a slight difference between this point and this point. Here you have the exit velocity, and you will assume that the velocity will continue. There will be no slight difference in the velocity, because the height is not also that there's no very much difference in height between those 2 points. So assume that the velocity will continue to be the same when we reach this point, and the point will be exposed to the atmospheric pressure. So this is the corresponding velocity, which is also the velocity in the pipe, because we assume this is the point, and it has the same velocity as this point. But only the difference here, this point is exposed to the atmospheric pressure, while this point has a certain pressure inside the pipe. So we can say that this velocity is the velocity inside the pipe. Okay, now you have the velocity inside the pipe. You can find the volumetric flow rate, right? Because you are given the area of the diameter of the pipe. So Q is equal V multiplied by A, which is equal to, what is V? V here is 8.52 multiplied by pi. Where is D? The 3 centimeter, which is 0.03 meter squared by 4. That is equal to 6.02 multiplied by 10 to the power negative 3. Okay. Now you have the volumetric flow rate. Now we need to know what's the this is the volume of the tank. Now I have the volumetric flow rate. Okay. Now the volume of the tank is equal to the cross-section, the base cross-sectional area multiplied by the height. Okay. So the height of the tank is 0.7 and the area, the base area is 4. Okay. So here 4 multiplied by 0.7. And here you have the time. You can find it by dividing this one by this one. Okay. What else?